Okay.
Yeah, that's all good. Hi, everyone. Welcome to the last GOCC of this academic year. We're very happy to close the year off with Danai. Before we get started, I'll remind us all about our community agreements. It's that everyone's learning, no one knows all the answers. And I'm trying to do this from memory and I cannot remember the last one of them, which is crazy. But anyway, take it away, Danai.
Yeah, thank you all for coming. So I'm going to be talking about colored multiset Eulerian polynomials. This is some work I'm finishing now with Han, who was a postdoc at KTH, where I'm also based in Sweden, and Liam Solus, who is my advisor at KTH currently. Right, so you've all heard about the Eulerian numbers and the Eulerian polynomials, right? This is the sequence of the first terms of these polynomials. So they appear like when thinking about integer points in polytopes, specific families of polytopes, when you're considering volumes of slices of certain slices of cubes, like the hypersimplex, and when trying to enumerate faces of simplicial complexes, right? And one way to think of them is that as the descent polynomial of permutations. So descent is a statistic of permutations. So if I have a permutation of n numbers and the ith entry is greater than the I plus 1th entry, this gives a descent. Then we collect this information in a polynomial, and that's the descent polynomial here. And we're gonna, and the Eulerian numbers is exactly this polynomial. The Eulerian polynomial is this polynomial, right? And again, here I want to emphasize that by bracket n in the slides, I mean the sets of numbers from 1 up to n. Right, so there are several. You can already see from the sequences here that the coefficients appear to have nice properties, right? They are palindromic, so the vectors of coefficients are symmetric with respect to the middle here. They are unimodal, so they increase up to some point and then they drop, and so on. You can check the roots that they're not very real. So that's what we're going to be talking about, but in a more general setting. And these numbers have been around for long, so they've been studied the bunch, and their identities known about them. One of the main ones is this identity here that has the descent polynomial on the left as the numerator and associates it with this nice generating function here, t plus 1 to the n. Right, so you may have seen this identity or other identities involving them. We will talk a little bit about some generalizations in that direction. So an overview is that we're going to talk about permutations, but this time, instead of regular permutations, we're going to think of multiset permutations, perhaps with colors, and their descent polynomials that are defined based on this statistic, and the generating functions that come with them. We will see that, and how they connect to the theory of polytopes and Erhard theory, and use this connection to derive results about the distributional properties of these polynomials. Okay, so to get started, I'm going to start with the definition of colored multiset permutations. So you all know permutations, right? We denote the set of all permutations of n elements with Sn. Now I can think about a multiset instead and permute its elements in turn. So by multiset, I mean it's a set where every number from 1 to n appears at least once. So it appears with multiplicity mi, where I is greater than 0, everything from 1 up to n. And then I can denote by Sm and think about all permutations of this multiset, right? Written in one-line notation, for example, right? So if my multiset is the set with 2 copies of 1 and 1 copy of 2, the multiset permutations will be these three permutations here: 1, 1, 2, 1, 2, 1, 2, 1, 1. Good. So now, if there are no questions about the multiset permutations, we can add colors to this idea. So to think about colorings of permutation, well, since I'm going to be adding a color to each entry, I'm going to need a vector of possible colors, right? So here by R, which is a vector of non-negative integers, n in total, I need one integer per number of the permutation. So from 1 up to n, that will tell me how many colors will I allow the ones to take, how many color options will I have for the copies of 2, and so on. Great. So now with this, if we have such a vector, a color permutation will be similar to permutation, but with a vector here, the vector of colors, that is a choice of some entry between 1 and rk for each k. So in other words, it's going to look like the regular permutation in one line notation, but I'm going to attach here in the exponent C1 for the color of the first entry. So C1 will be the coloring of the first entry, C2 the coloring of the second entry, and so on. And if the first entry, for example, is equal to k, that means that C1 will take values from 1 up to rk. So the possible colors that are available. We'll see examples. And at the end, this is just a technicality for the statistics to work out. We're gonna attach one more term of at the end of the permutation. So I'm gonna attach pi m plus 1 with the smallest possible coloring. So pi m plus 1, sorry, will be n plus 1, which is a number that was not used so far, with the coloring 1, the smallest possible coloring. So that's just something to add at the end. And we'll denote this whole set by Sm to the r. So for example, here's again the definition. If I choose both the colorings to be 2, for the color vector to be the vector of 2's here, right, I'm gonna choose a multiset saying one containing 2 copies of 1, 2 copies of 2. I'm gonna get all possible permutations. Well, firstly, the colors of the 1s and the 2s can be between 1 and 2 here. And always I'm going to have a fixed 3 with the color 1 at the end. That's just by the definition again. That I'm going to ignore for now. And I can also, instead of letting the colors vary, I can also consider all permutations of 1s and 2s here. So I haven't put this in the picture, but if I continue, I'm going to have to eventually go through of all possible permutations of the multiset 1, 1, 2, 2, and all possible colorings to give them. So that's going to be in total 6 for the permutations and 2 to the 4th for the 4 entries of the permutations and how I can color them. Right. So already for this small choice of colors, I get a lot of them. Right. And this is also called the signed case, signed permutations, because, you know, instead of giving just 2 colors, you can think of 2 signs for each entry, plus and minus. And that's how else it's known in the literature. Is this okay? Great. So now I am interested in descents. And descents, again, is an entry of the permutation of this colored permutation of multisets, such that the value drops from the I to the I plus 1th entry, right? But to make this comparison, what I need is an ordering between all possible elements that can appear. So all possible elements with all possible colorings need to be ordered in a total ordering. So I need to make this choice. There's a couple of standard choices in the literature, and we're using the one that is due to Steingrimsson. If you change the ordering, the results are similar, but there are some changes to be made in the in the indices and stuff. But in any case, so the ordering we're using is that we order, if the colors are the same between 2 numbers, the largest number wins. So n with the first color is greater than 1 with the first color. And if the colors are different, then the entry with the highest color is larger. Right, so that's our standard ordering. In the example, you can see that already. So here, if I consider again the same multiset with the same coloring, this is what the ordering will look like. Again, I put the 3 to the 1 here, not because it's an element of the multiset, but because it's something I have attached to the end and I want to be able to compare it for the descent notion. Yeah, and using this ordering, I can go to, here are some examples. I can go to this permutation and think the first entry, 1 to the with the color 2 is greater than, with this ordering, the second entry, 1 with color 1. And that gives a descent. And the fourth entry, 2 with the color 2 is greater than 3 with the color 1, for example. That gives another descent. Right. So that this permutation has 2 descents. And so on. These are some examples. So you can already see, you can have 0 descents, 2 descents, 3 descents. So it makes sense to consider these options. And for this, I define the set, let's say des with capital, to denote the set of descent entries, of descent positions for the permutations. And by des small, I denote the number of descents. So doing that, I can again form a polynomial where each permutation, each colored multiset permutation contributes the term x to the number of its descents. And this is what's called the colored multiset Eulerian polynomial. So this generalizes the standard Eulerian polynomials because I restrict to the non-multiset case, and the non-colored, I get back the Eulerian polynomial. Right, so it's a direct generalization. That's what we're going to be interested in. And here are some examples of what this looks like with this notation. So if I'm in the uncolored case, so R equal to 1, 1 means no color for the first one, no color for the second one, just one color option, right? So on the uncolored case. And then I have the multiset with 2 copies of 1 and 1 copy of 2. With our notation, all possible permutations are these. So 3 to the 1 attached at the end. All the colors are equal to 1. So then if I think of I can find the descent polynomial and form it by putting 1 in front of x to the 0, because there is only one permutation with 0 descents. So x to the 0 will only appear 1 in this polynomial. And there's 2 permutations with 1 descent, namely this one, the underlined one. And so that's going to contribute 2 times x to the 1. Right, so that's how I form my descent polynomial here. And yeah, there is another more complicated example here. So, I mean, not so complicated, right? If I take the multiset with only 2 copies of 1s and 2 copies of 2s, but I allow two colors for the first, for the 1s, and 1 color for the 2s, then these are all the possible permutations. And again, I get the descent polynomial written here. So 1 is always in the beginning the coefficient of x to the 0, because there's only one permutation with 0 descents. And then I get 13 with 1 descent and 10 with 2 descents. But you can already see from these examples that it's not a fact anymore that the coefficient vector will be symmetric. There's no palindromicity here. So on the other hand, there is the unimodality, there's the real-rootedness. So the question would be to investigate these polynomials a little bit more and see when it holds, when holds what, basically. Right, so let me know if there's any question on the definition of descent polynomial. So as I said, we are interested in studying this colored multiset Eulerian polynomial as a polynomial. Let's say its degree is d. And we want to understand things about this distributional property. So whatever you're familiar with, palindromic, unimodal, log-concave, gamma positive, real-rooted, or other more technical terms. And if we understand these, we would look at this. We can also look at the symmetric decomposition and ask the same questions. So whenever I have a polynomial of degree d, I can always find a unique symmetric decomposition for it. And by symmetric decomposition, I mean one polynomial A here of degree D, the same as of my polynomial, that is palindromic. And I can write in the form A plus X times B, where B is also palindromic and it has degree less than D. So there's a unique way to construct sets A and B. And these A and B are often interesting. They often appear we will also see in the talk examples where they connect to permutations as well. So it's interesting also to understand these two polynomials. If the colored multiset Eulerian polynomial is palindromic itself, then this decomposition is trivial. The B polynomial is the zero polynomial, and the A polynomial is the same as our colored multiset Eulerian polynomial, right? So this is not a very interesting example, but in the rest of the cases that is not palindromic, that we will see there are many, we can also study this symmetric decomposition, right? And here, for example, in the notions, I will emphasize gamma positivity. So if our polynomial can be expressed in a certain basis, and the coefficients in that basis here, the gamma i's, are non-negative, we say that it's gamma positive. And necessarily, if this happens, our polynomial is palindromic. So only palindromic polynomials, for palindromic polynomials, it makes sense to ask about gamma positivity, right? If our polynomial is not palindromic, what I can do is look at the symmetric decomposition, the A and the B that always are palindromic, and then try to see if they are gamma positive. And if they're both gamma positive, then we say that our original polynomial is bi gamma positive, right? So just in case you haven't seen this. Right, so how do we go for proving all these properties? Yeah.
Danai, I think there's a question on the previous slide.
See this.
No, it's all good. I'll ask it for you. Is the symmetric decomposition unique? Yes.
Okay, yeah, thanks for the questions and the comments. So, and please, I'll leave it to you, Anastasia, to interrupt if I don't see it because it doesn't appear. So yes, this decomposition is unique up to D. So if you want it to have the same degree here as your polynomial, it's unique. If you increase it by 1, there's another unique symmetric decomposition, and if you decrease it and so on.
So is it unique for all polynomials?
For what, all?
All polynomials, like can I decompose any? Okay, cool.
From what I know.
Okay. Yeah.
Well, it's an exercise to try and prove it, but the idea is you if you start with these coefficients, it's gonna tell you how you can write it as a combination of these coefficients, the A and the B, and that's why it's unique. But it's non-trivial to see it, of course. So now we're gonna see how we can prove many of these properties at once, right? And we're gonna use this tool called interlacing theory. So this is not a hard definition. So if we have two polynomials, P and Q, and they all have their zeros that are real numbers, right? Say the AI's and the alpha i's and the beta i's. Then we're saying that Q interlaces P and denoted that like Q smaller than P if there's this if the roots basically alternate, right? So I can express the roots in this way. You can also see the example here on the graph, and that's the intuition. That's when the Q interlaces P. For example, if I consider this, again, Eulerian polynomial, 1 plus 4x plus x squared, with this other Eulerian polynomial, 1 plus x, with 1 degree less, then the roots of P sort of sandwich the roots of Q, right? So the interlace, and that's a strong property. Whereas a non-example would be these two polynomials, P and Q on the right, in which case P has no real zeros, doesn't have real zeros. And so therefore we cannot even talk about interlacing. And we'll see that both these polynomials arise as polynomials of the symmetric decompositions we consider. That's why it's interesting. Not everything is interlacing. We will use that to see it. So yeah, going back, it's just a strong theory, because if B, in the symmetric decomposition here, the polynomial B of the smaller degree interlaces the A, and they have non-negative coefficients, then all of these properties follow for free. And so, except for palindromicity, everything else, like our color multiset Eulerian polynomial, will have all the other properties. And not only our polynomial, but also the A polynomial in its symmetric decomposition and the B polynomial in its symmetric decomposition as well will have all these properties. Right, so the goal is to prove that for some families. Right, so now on that, let's see some examples, why it might hold or not hold. So here we saw earlier this example of multiset and coloring that gives us this colored multiset Eulerian polynomial that then we can break into the A and the B in this way. So A is going to be 1 plus 4x plus x squared, and B is going to be 9 times 1 plus x, what we saw earlier. And we saw that B interlaces A just now in the example, right? So in this case, for this example, the interlacing property holds, and this polynomial has all these properties, the distributional properties we wanted to satisfy. Whereas there's another example, very interesting, a multiset with 5 copies of 1 and 2 copies of 2 here, no colors needed in this case, where if I think of this, take the symmetric decomposition here, it's going to be what we saw before. One of the polynomials does not have real roots. They don't, hence it doesn't have the strong interlacing property. It doesn't have the B does not interlace A. However, it might have other interesting properties like alternatingly increasing, which is the same as saying the A's and the A and B polynomial that are non-negative are unimodal. Right, so it still might have nice properties, but not everything satisfies this strongest property. Even in the uncolored case, right? So now this is a little bit more technical. So how do we go for showing this property? So our first step would be to generalize the Carlitz identity from regular sets to colored multisets. So if you combine what's known in the literature, basically what was known is that I have written it down in the table here, where the colors is this, the columns correspond to colors, and now I'm thinking only about fixed colors. So that means all the colors are equal to 1, all the colors in the first column, all the colors are equal to 2 on the second column, and so on. That's what it means. And here I'm thinking about sets, multisets, where all the multiplicities is equal to 1. That means the first row corresponds to the regular multiset, the regular sets. The second row would be multisets with 2 copies of everything. Third row, and so on. Right. So it turns out MacMahon has showed that this Carlitz identity holds more generally for multisets and in the uncolored case. And Lee gave some formulas in the signed case. And as well, it has this nice formula that you see. So every time I increase the cardinality of its multiplicity, I essentially just add 1 term to the product here. So it's really nice. Right. And Steingrimsson, on the other hand, had shown the same identity that it generalizes for colors of regular permutations, right? So the one in front of the T here, when I think of two fixed color vector equal to 2 becomes a 2, 3, and so on. So what we did is just to generalize this simultaneously to colored multisets. So it turns out that, yeah, as expected, we get this more general theorem where if you increase both the multiplicities in the multiset and the color, if you take any color vector the same expected identity will hold. So this is the theorem here in more generality. So that holds even when not all the color vectors are fixed. For example, they can also have its coloring for its entry can vary with each other. It's still gonna hold. And what happens on the left-hand side is that we have the colored multiset Eulerian polynomial, and on the right-hand side, I have a product of n different things that each captures the color here and the multiplicity in the multiset for k, and for its k from 1 to n. Right, so in particular, if I specialize here all the nk's to be equal to 1 and all the rk's to be equal to 1, then I recover Carlitz identity. Right. So this is a formula we needed to derive in order to continue and connect everything to polytopes and so on. And we couldn't resist giving a multivariate generalization that you don't have to look at, but it looks really nice, even for many variables. And as you can see on the right-hand side here, it's just, now I'm thinking, what was this with Q? Yeah, now I'm thinking of this as being ZK or Q in general here, the Q binomial coefficient instead of the standard binomial coefficient, right? So this connects back to some identity of Cho and Gesell when I specialize in a certain way that involves not only the descent statistic, but also some colored multiset analog for the major index of a permutation. If you know what this is, another statistic, but it does give a nice specialization. And well, if I specialize a lot, I get what we needed. I get this identity generalizes the Carlitz identity. Right, so in case someone has seen this other identity that looks very similar, they shouldn't be confused, because there's also this identity, right? There's this actual Carlitz identity that involves the descent polynomial and the major index on the left, and then there's a similar generating function on the right. But anyway, it's not, I don't want to get into too much detail, but there's another story there, and there is another multivariate generalization in that case. So don't confuse it with this. The cool thing about this generalization is that the right-hand side of whatever this is does not depend on the color. In each of all of these equations, even in the first one, it does not depend on the, I mean, the first one doesn't have any colors, let's see. But in any case, the last one does not depend on the color. So whether you fix the color vector to be all equal to 1, all equal to 2, and so on, it's gonna equal the same thing. That's really cool. But that's another identity. Right, and with this being said, we can switch back to our problem here, which is again colored multiset Eulerian polynomials that are the descent polynomials of colored multiset permutations, and their symmetric decomposition here with A and B palindromic. I want to understand their distributional properties. And now I have this new tool, the formula that we just saw that I could use, right? And yeah, so well, there's a state of the art here of what has been shown in terms of distributional properties for this polynomial. But what's important is that for the non-multiset case, Brandten and Solus showed this property that B interlaces A in this case using polytopes. So basically, we want to do a similar idea, but for a more broad class of polytopes and permutations. So that brings us to the theory of polytopes now. Right, so I think you must have all seen polytopes before. They arise as the convex hull of finitely many points in RD, or as a bounded intersection of finitely many half spaces. So for example, you can think of the cube as arising as the convex hull of its 8 vertices. And similarly, if I take any finite collection of points in R3, I'm going to get the polytope. If you haven't seen them, you can think of them in this way, right? So given a polytope, the most standard example of polytopes is maybe the standard simplex, right? So that means the convex hull. Yeah, by convex hull, I mean, I take in this case, 2 points in the plane, and then I take the line between them, or more generally, everything between them, every convex combination of these points, right? So the convex hull between the unit vectors here in R2, it's this interval, and we denote it, it's the standard simplex of dimension 1, delta 1, right? Then if I think in R3, I'm going to have the convex hull of 3 points. It's going to be of 3 unit vectors, delta 2, and more generally tetrahedron and so on. This is the simplex. This is the general definition of the simplex, the standard simplex. So that's what I mean by it. And when I talk about dilated polytopes, I mean take all the points of the polytope and multiply them by k. And this again gives you a polytope that's called the kth dilet of your original polytope, right? So if I take the first example here, the simplex of dimension 1, and I take the second dilet, then essentially it's the convex hull between the unit vectors in R2 multiplied by 2. Okay? Right, so now to bring in Ehrhart theory, I am interested, like the Ehrhart theories, they start with a polytope that has integer coordinates. Here, it's the convex hull of vertices with integer coordinates. And we want to understand, when we look at the kth dilet of the polytope, how many integer points there are. Right, so I look at this intersection in the kth dilet, and I call this value, the number of points, the Ehrhart polynomial evaluated at k, or Ehrhart k. So Ehrhart, in fact, showed that this function is a polynomial. And yeah, and therefore that I can talk about the Ehrhart polynomial. And it's such that if you evaluate it at k, it gives you the number of integer points in the kth dilet of the polytope. Right, so for example, if I think of the standard, the simplex of dimension 1, here I want to look at points in dilets, right? 2 integer points in the first dilet, 3 integer points in the second dilet, and so on. You can already guess that the Ehrhart polynomial on k would be k plus 1, right? And more generally, even if I thought about the second dilet, fourth, and so on, I would be rk plus 1, and so on, right? And if I think in a higher dimension of simplices, again, you can use some counting argument, some stars and bars argument to understand that the Ehrhart polynomial would be k plus d choose d. Or if I think of dilets, again, the r comes in front of the k. So these are some first examples. So some other well-known example is the cube, the square and the cube more generally, right? So the square, you can already count from the picture. The first dilet is going to have 4 points, 2 squared. Second dilet is going to have 9 points, which is 3 squared, and so on. It's k plus 1 squared, or more generally, k plus 1 to the d. So where am I going with that? Like, why is the square is basically a product of 2 intervals. So that's the idea. So in general, if I have some simplex here, delta m1, which for the square it would have to be the interval, and I dilate it with something, and I take the product with another dilated simplex of some dimension, and so on. So I consider the polytope that is a product of dilates of simplices. And by product, I mean the points of that polytope would be the Cartesian product of the points of the respective polytopes in the product, right? Then what happens to the Ehrhart polynomial is that it factors nicely as the product of the Ehrhart polynomials of the respective dilated simplices. So that's why in the cube case, the cube was a product of intervals, and that's why I had the power there. I had k plus 1 to some power. Right, so that's the idea here, that basically this formula that we saw earlier allows us to realize the generating function here as the Ehrhart polynomial of the polytope. And for those familiar with Ehrhart theory, that means the H star of that particular polytope, the H star vector or polynomial, would be the colored multiset Eulerian polynomial as well.
Here we go. We got go back to the start.
To the what?
That sounded like an accidental.
Oh, okay, good. Right, so yeah, anyway, why is this interesting? It is because we can use this first of all, it's nice that Eulerian numbers, you know, they are known sort of to correspond to H star, to like Ehrhart, to be in connection with Ehrhart polynomials of cubes, the Eulerian polynomials and the Ehrhart polynomials of cubes. What this is saying is that if I consider multisets instead of regular sets and look at their permutations instead, I'm going to be thinking about products of simplices instead of just products of intervals. And then if I add the colors to the permutations, I'm going to essentially just dilate my simplices. Everything is captured there in the geometry of those objects. Right, so, but also, we can use this to conclude the interlacing property that we wanted. So it's easy, now that I have a polytope, it's basically, as long as it has an interior point, which happens if I restrict the colors to not be, the color vector to be not too small, to be large enough, then directly I can prove that the B polynomial interlaces the A polynomial. And it's also easier to see exactly when these polynomials are palindromic by the structure of the polytope. So let me explain this here a little bit. I'm not going to go through the proof, so feel free to read if you're interested. But basically, what happens is that we studied basically above this diagonal, the polytopes in this table, and more generally when the color vectors don't have to be fixed, equal everything to the same value. But anyway, so we found exactly which ones are palindromic, and they are the ones in the diagonal. And then we show that everything above the diagonal is not palindromic. And furthermore, it has the property that B interlaces A. I mean, all of those polynomials have the property that B interlaces A. So they're all unimodal, real-rooted, gamma positive, or bi-gamma positive in this case. Right, so that's where we are. So we didn't study this family under the diagonal, but only everything above this diagonal. So given that, yeah, I don't know. So for this column here, we do know not everything is for sure not everything is gonna have the interlacing property, because there is an example that we already saw of an uncolored polynomial that is not even bi-gamma positive, right? So bi-gamma positivity is not always there, but sometimes it is, and that's what this next theorem says. So this is just some specialization for those interested. So if I select a multiset, a particular one that has all the copies, everything having the same number of copies, and I attach n+1 to the end, and then I also consider the multiset without the n+1 attached, so the regular multiset with everything the same multiplicity, then this polynomial, in this case, turns out to be bi-gamma positive, so there's a proof of that. And in fact, That's what Lin, Mama, and Zhu proved. And they also even gave a combinatorial interpretation for the gamma coefficients of the B polynomial in the symmetric decomposition. So they thought, since it's by gamma positive, the A and the B are gamma positive, and the gamma coefficients of the B polynomial do count something. So they expressed what they count in terms of weakly increasing trees. So something that we did is express also the gamma coefficients of the A polynomial in terms of some other weakly increasing trees, right, with certain properties. And now the question would be, what happens more generally with the gamma coefficients? Can we find a combinatorial interpretation for the gamma coefficients? So taking it back to the previous picture, we had a bunch of polynomials here in that diagonal that we saw, that they were symmetric, palindromic, and everything above the diagonal was not palindromic and by gamma positive. So there's a lot of A and B polynomials to study there. So one question we have is, can you find a combinatorial interpretation for this gamma coefficients here? Because what has been done here in the uncolored case is, in the few cases that are known to be by gamma positive, there is a combinatorial interpretation for the gamma coefficients. Right, so with this in mind, how do you generalize this to colors, basically, because multisets are here, colors are here, so we need to find a way to think about those. So that's one thing, right? So this is an example of what this would look like, instead of giving you the definition of weakly increasing trees and what they look like. So if I take this fairly small set, it's the smallest interesting example. So 2 copies of 1, 2 copies of 2, and then we attached one thing at the end, a 3, like we attached n plus 1 earlier, uncolored, right? So the descent polynomial can be split now uniquely into these A and B polynomials here that are both palindromic, right? And then using these two theorems from before, I can express it. Here is the A polynomial in the gamma basis. So these are the trees that are counting them, gamma coefficients, and the B polynomial can also be expressed into those nice trees. So the question would be, how do I find the corresponding notion of trees when I add the colors more generally? Okay. So let me know if there's any questions on that. Otherwise, I'm gonna go through some last couple of examples of what kinds of polytopes also are interesting and connected to these color permutations. So, right, so you might have heard about the S-lexical simplices or polytopes in general, right? So given a sequence of non-negative integers, I can associate a simplex to it. And the simplex is defined by these inequalities here, like all the points lambda, where if I divide the first entry by S1, it satisfies these inequalities and so on. It also has a nice vertex description. But this is the inequality description here. So I wonder if this is strictly less than 1 or less than or equal to 1, maybe. In any case, these polynomials, I forgot that I didn't define the H-star vector here and put it, but whatever so these polynomials have these polytopes have an Ehrhart polynomial, and if I express it in a similar rational form as I was doing with my permutation, where I had the colored multiset Eulerian polynomial on top and below I divided by 1 minus x to the d plus 1, then I get on the numerator at this time, I would get what's called the S Eulerian polynomial. So Savaz and Schuster, anyway, studied, like, initiated the study of when the colored Eulerian, not multiset Eulerian polynomial for a fixed color vector can arise to connect with these S Eulerian polynomials. So when it's an S Eulerian polynomial, when can I find an S Lexer-Hall simplex whose Ehrhart polynomial will be the same as the generating function associated to this colored multiset Eulerian polynomial, right? And they first studied the case where the multiset has one copy of everything, so the standard sets. And for any color, any vector of fixed colors, they found that this happens. So there is a sequence, namely the sequence from 1 up to n, that satisfies this. And they also found another interesting example. So the multiset with 2 color copies of everything, but where there are no colors. And conjectured that also when I have the signed case of the same multiset, there's going to be an S sequence that does it. So it was proven later by 2 sets of authors that even when I consider the signed case here, the multiset with 2 copies of everything, I'm gonna get an S Lexer-Hall simplex that comes with it. So more generally, the question would be, can I generalize this to all multisets and all colors? And the answer is no. You can generalize it to colors. The same multisets that are known to have an associated S Lexer-Hall simplex can generalize to color vectors that are allow for more colors, but not directly to the multisets, because from 3 onwards, the nice relationship is gone. So that's why we use the products of dilated simplices instead of finding a suitable S Lexer-Hall simplex for our previous theorem. However, all of these polytopes we saw, they fall in a different family, which is a generalization of the S Lexer-Hall simplices called S Lexer-Hall ordered polytopes that contains both S Lexer-Hall simplices and ordered polytopes. And therefore, in a sense, it is a natural, what we found is a natural generalization of S Lexer-Hall simplices. It's just not a simplex, it's a polytope now. And to end, because we have no time. So one question would be, which colored multiset Eulerian polynomials are S Eulerian in fact? We found some examples, but can we classify them all, or can we find more examples and understand their symmetric decomposition in this way? And what distributional properties will they satisfy, right? And similarly, I'm not going to go through this, but the uncolored case of, maybe it's here, the uncolored case here will correspond to not dilated simplices, so just products of simplices, which are known as order polytopes, right? So in the uncolored case, the multiset permutations would correspond to order polytopes. So this gives a new proof of why they would be palindromic. This would follow by the properties of the poses associated to the order polytope and so on. So that would also be interesting to study more and maybe generalize. And this, it's about time to end, 1 minute past. Yeah, we hope to continue pursuing this. Thanks for your attention.
Thank you. This is so interesting. Any questions? I'm trying to process this slide still, but I might have questions on this.
Mm-hmm.
I'm curious about this last point. What interesting polytopes have you found that have interesting, cool families?
Okay, so since you asked, what we're looking now with Matthias Beck is so what happens if you take subpolytopes of your polytope corresponding to a certain set of color permutations and your or just we had multiset permutations, and your sub-polytope is nice, and this can imply this can give nice connection to certain families of multiset permutations, and it connects nicely to certain pattern avoiding multiset permutations.
Nice. Okay.
A good question.
I had a different sort of question when you mentioned the interaction with all of the polytopes. One of the things that you get, one of the ways that you can get the multiset Eulerian polynomials without colors is to get the Eulerian polynomial as the H vector of the permutahedron, and then take a quotient of the permutahedron, or like you can take a quotient of the complex essentially, and then the H vector of that quotient would be the multiset Eulerian polynomial if you took the quotient from like a Young subgroup, right? And so is there a way to interpret these colored versions as either some sort of quotients of a bigger complex that corresponds to colored permutations, or is there some sort of relevant approach there?
Yeah, that's a good question, but I don't know.
Maybe for now, let's thank Danai again, and I'll stop the recording.